So in section 4.3, we're going to be talking about something called Riemann sums. Riemann was a mathematician, and he decided that he would want to find the area under a curve in a more exact way than finding just rectangles. So first of all, in this first part of 4.3, we're just going to familiarize ourselves with the notation that Riemann chose to use. In finding the area under a curve, instead of saying, please find the area under the curve y equals x plus 2 between x values of 0 and 3, he used this notation with that integral sign that we've been talking about. So this integral sign is Riemann's way of saying, find the area under this curve. So the integrand here is the curve, or the straight line in this case. And then between the values of 0 and 3, so this is the a and this is the b that we've been talking about when we talk about the interval. So before we talk about the method that he came up with to find the area under the curve, we're just going to get really familiar with this notation, that this means find the area under the curve. And then we're going to be using simple geometry shapes to find the area of under. So this integral from 0 to 3 of x plus 2 dx asks for the area of the trapezoid, the area under the curve x plus 2 from 0 to 3. So if we want to find that area, we just need to find the area of the trapezoid. You can talk about this being base 1, and this is base 2, and this is the height. So it's like we have a trapezoid on its side. And the area of that is base 1 plus base 2 divided by 2 times the height. Or we could break it up into a rectangle and a triangle, but let's just use this formula. So base 1 we can see from the graph is 2, and base 2 we can see from the base 2 we can see from the graph is 4 over 2 times the height. So in this case this is 2, so doing the math we get an area of 6. So the integral of x plus 2 from 0 to 3 would equal 6. Alright, so if I give you the picture of a region and I ask you to set up a definite integral, by the way, it's called a definite integral because it's different than what we've been working with so far because it has numbers here from 0 to 3. What we've been doing so far didn't have any numbers there, just the antiderivative. So now we've got numbers here. That's what makes it look different than what we had before. So if it says set up a definite integral that yields the area of the given region, we need to find the equation of this line. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the y-intercept is 10. And it goes down to 1, 2, 3, 4. So the slope would be 10/4. Sorry, negative 10/4, down 10 over 4, which reduces to negative 5/2. And then our y-intercept is 10, so y equals mx plus b. That's the equation of that line. And we want to find the area. Area equals the definite integral of the equation of the line with respect to x in this case. X is our variable of integration from 0 to 4. So these are x values. These values would match the variable of integration. So that's the answer. Set up the definite integral that yields the area of the given region. That's what we just did. Okay, what if they ask you to sketch the region whose area is given by the definite integral? They're still working with, do you understand what this notation is asking? So what this means is this is the equation that we're trying to find the area under. So we'll graph y equals 3. Didn't quite hit that line. Let's say that's 3. From 1 to 4. So we only want the region from 1 to 4 under the curve. So it's this region here. And then use a geometric formula to evaluate the integral. Well, this is a rectangle. So what's the formula of the rectangle? Actually, it's a square. It's got a width of 3 and a height of 3. So 3 times 3 is 9. So that integral would equal 9. That definite integral from 1 to 4 would equal 9. If you want to sketch the region and find the area here, that region is a semicircle with a radius of 2. So it's going to be just the positive part of the circle, because it's only a positive square root, from -2 to 2. So they're asking for the area under the curve down to the x-axis from -2 to 2. So the area geometrically would be pi r squared, but only half of that. And our area, our radius is 2. So we have 2 squared, which is 4. So the area is 2 pi. So this integral would equal 2 pi. Sketch the region and find the area sine x from -pi to pi. Looks like this. Goes up to +1, down to -1. From -pi to pi, so we want this region. And remember we talked last time that the region under the x-axis is negative and the region above is positive. So whatever these areas are, they're not exactly circles, so we can't use any geometric formulas. But we can see that they're equal regions, and one's negative and one's positive. So whatever this one is, and whatever that one is, they would match and add up to 0, because we can add up the two regions, just like geometrically you can add up two regions to find the area of the whole thing. So that would equal 0. If we want to find the integral from 0 to 5 of 2y dy, this is the line 2y, and it's with respect to y, so everything is based on y values. The 0 to 5 here is the y value of 0 to 5. It's still a triangle, so we can use a geometric formula to find the area. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 by 1, 2, 3, 4, 5. So the area, since it's a triangle, is 1/2 base times height. So 1/2 times 5 times 10. 10 divided by 2 is 5. 5 times 5 is 25. Properties of definite integrals. We kind of talked about that a second ago. If you want to find the area of two different portions of a graph, you can add up the pieces. So if you want to find the area of the whole region from A to B, you can find the area from A to C, and then from that C to B, and add those two pieces together, and that will be the area of the whole region. There's a definition of two special definite integrals. If we have an integral from A to A, so think about what that means. If you're trying to find the area under a curve from A to A, so here's a function, here's the curve, here's A, and I want to find the area from A to A, so really to itself, there's no area there. From one x value to another, if the x value is the same, there's no area. It's just that line, so that area would be 0. Let me draw a figure of what this is talking about. If I want to find the area from here to here, this is A and this is B. If somehow this was easier to find the area of this piece here and then find the area of this piece here, we could just add those two pieces together to find the area. And we'll talk more about how that is helpful as we go on. Alright, and the other definition of a special integral, if you want to find the area from A to B of one function, how does that relate to the area, the area of the function from B to A? It would just equal the opposite. So besides area above the x-axis being positive and area below the x-axis being negative, area goes in the direction left to right also. So if you want to find the area of this curve from A to B in this direction, that would be a positive number. But if you're finding the integral from B to A, going backwards, that would be the opposite of whatever that other area was. So this usually is the lower bound. It's usually the smaller number. But if you change the order so that this one is a higher number on the bottom, then you're finding the area but it's going to be negative. It's going to be the opposite of whatever the positive area would be. Theorem 4.7 talks about a few more properties of definite integrals. Definite integrals follow a lot of rules, like derivatives that we've done and summation formulas. If you want to find the area under a curve from A to B of a function times k, you can just find the area of that region and then multiply that times k, multiply that answer times k. So a constant, you can either evaluate it with the integral and find it with the area, or evaluate the area piece first and then multiply it times the constant. Same thing with adding and subtracting. If you'd like to add two functions together and find the area between those two, the x values here, you can find the area of one curve and then the area of the other one, and then add the two pieces together. Or if you want to subtract the two, you can subtract them first and then find the area, or you can find the areas individually and then subtract them later. Those pieces will come in handy as we work more and more with definite integrals. But remember, today we're just using this notation of definite integral to understand area under a curve and using simple areas that we can find geometrically. So we're finding areas geometrically, or using the knowledge of things above the x-axis being positive and matching things below the x-axis would be negative. Later we'll talk about how to actually calculate the area under a curve without having a geometric formula. So your homework is page 278, 1 through 21 odd.